Okay, everyone, let's now finally move away from two-terminal devices such as diodes, two terminals, just two contacts, and now finally start to look at three-terminal devices, which are transistors. The first transistor we're going to work with is going to be a bipolar junction transistor. The reason why we're starting with these bipolar junction transistors, or BJTs, is because they're based on two back-to-back PN junctions. So it's a great natural extension of what we learned for diodes. The photo to get us started here is of the first transistor. The first transistor was invented in 1947 at Bell Labs. And if you look at this thing, you'll start to see where some of the terms we're going to use today come from. And so the first thing that you notice about this thing is it's like any new invention. You've got a spring, you've got some kind of material here, you've got crudely assembled wires here. And so this is what it's like when they made the first transistor. But some of the things you'll see in terms of terminology for BJTs is we'll see something called a base. Well, that term comes from the first transistor, where this base here is a slab of germanium semiconductor. This was way back then you didn't have nice semiconductor wafers, so this is the best chunk of semiconductor they could get access to. And so that was the base of their setup, hence it's referred to as the base in a BJT. The other parts of this, the emitter and the collector, are also terms we'll use for BJTs, and the emitter is going to inject the carriers into the device, and the collector is just going to collect them out, basically. And so that's where those terms come as well. And you'll understand more as we go through them. Again, note, anything starred in this lecture is a potential quiz question. Before we go into the BJT and how it works, let's look at some of the historical stuff behind this in terms of why we have the name transistor. And so this is a memoranda that was passed around Bell Labs right after the technology was invented. You can see the date, May 28th, 1948. And the subject of the memoranda was to get terminology for semiconductor triodes and to basically get committee recommendations. Ask all these folks, what are we going to call this new invention? And so it says here, recommendations are made for an equivalent circuit representation and terminology relating to semiconductor triodes. And I think it's interesting to look at historically what some of the names they were thinking. So, here were your choices. You could designate in order, first to third priority in terms of rank order. You could have chosen back then semiconductor triode. So it's made of semiconductor material, and it's got, unlike a diode which has two contacts, diode, a transistor has three contacts, hence triode, right? They called it a surface states triode, crystal triode, solid triode, my personal favorite, iotatron, and the last one was transistor, which I think was named because it basically was able to transform resistance somehow. So if you could use voltage or current to transform resistance, that could affect current flowing through part of a circuit, and that's basically what you get with transistor action. And so we know the history. They chose transistor, and sadly, iotatron was not the name they chose. Okay, so here's a BJT. Okay? And we'll start to break this down bit by bit, so don't become overwhelmed when we first look at this, okay? But if you look at the BJT, it's two back-to-back diodes. Here's a PN junction, P-type, N-type, and here's a PN junction on this side, okay? And here's the depletion region here. Here's the emitter, here's the base, here's the collector. We've got voltage sources and currents, okay? Now, if we look at a circuit symbol for a BJT, you might recognize it as follows. Here's the base, here's the emitter, and here's the collector. And of course, if I have all these currents coming into one node of a circuit, the currents all have to sum up as you would expect for a simple network like this. Now, here's how we're going to break this down. We need to review diodes first because this is based on diodes. And so the first thing we're going to do is we're going to look at the reverse bias diode, which is the collector. So if you look at this diode, wide depletion region, that's because it's reverse biased. And so that's why if it's reverse biased, you can see the current flowing through this device from emitter to collector. For the collector is flowing out by drift current because it's reverse biased. Then we'll next look at the emitter, okay, which is a forward bias diode where I have a high concentration of holes. I reduce this barrier here, and then they can diffuse over into the base. And then lastly, what we'll try to do is figure out, what does the base do? Why do I need a base in here between the emitter and between the collector? And so let's do this in terms of diodes, and everything will start to make sense. Okay, so starting with the collector, we know it's going to be a reverse bias diode. So if you recall, for a reverse bias diode, all the current was basically driven by electric field. So if I had minority carrier holes, which were created by thermal generation of electrons that leaves behind a hole, if it's close to the edge here, it's swept across by E field, drift current. And the same thing on this side. If I have minority carrier electrons here, which were thermally generated, if they're close enough to the edge, they will also be swept across as current. Well, we want the exact same thing for a BJT, we'll see, but the difference will be that we want to have basically an increase in the number of the electrons and holes we have near the edges here. So, the collector of a BJT is a reverse bias diode that collects minority carriers brought to it. And so the question is, how do you bring these carriers right next to the edge of this reverse bias diode? Well, that's where the emitter comes into play. What it's going to do is it's going to emit carriers that can be collected by the collector. And so the emitter will basically bring carriers into here, which then can drift out the collector. And we'll find that the emitter is just a special forward biased P plus N diode. And let's review that now. So let's look at what the emitter will look like. Again, the emitter is going to be a heavily doped P side, lightly doped N side. It is forward biased. It injects current by diffusion from the emitter into the base. And here's why we want to look at it and have it be P plus N. And so remember when we looked at current through the diode, we did current through the whole diode. We said that the current through any loop is obviously constant. So if we map our current across this diode, okay, then way out here we have nothing but holes. So this is all holes. And then as we get closer to the edge of the depletion region, here I'm diffusing holes over to the other side. And then the whole current goes down. As these holes show up in N-type material, they're recombining with electrons, right? And there's also electrons coming this way. If I go way out to this end, it's all electron current. And the current comes in, and most of these electrons here are just coming in to recombine with the holes I brought over. And by the time the electrons get to the other side, there aren't many electrons because most of the electrons have recombined with all these holes I'm diffusing over this way. Now, here's the key point. Because it's a P plus N junction, hole current dominates across the junction. There are way more holes going this way than there are electrons this way because there's a lot more holes available to diffuse over, right? More importantly, okay, you'll notice that hole current here dominates over electron current out to a certain distance. So not until I get about right here, okay, do I start to see electron current start to dominate. And so up to this point here, up to this point, the hole current absolutely dominates. That's going to be really important because this is going to be the base region of a BJT, and the hole current dominating is going to be critically important. Okay? So, I think at this point now we're ready to make and understand a P plus NP BJT. So let's take a look at this. So, now let's make our full BJT. I'm going to join together P plus material, lightly doped N-type material, and lightly doped P-type material here. And one thing we're going to do is we're going to keep the base width here very thin. Remember, the middle of this thing is the base. Okay? So, let's look at the band diagram as well here. So, again, here's my P plus material here. So notice, of course, the Fermi level is closer to the valence level for the P plus material. Here's my base, it's N-type, so Fermi level is closer to the conduction band here. Here's my depletion region where the bands bend in between. Here's my base width, which is the width of the N-type material that is not depleted. Okay? and here I have my lightly doped p-type collector out here, and you can see it's p-type as well. And so you join the bands together and you get this sort of shape. And of course this is n-type material, so I have electrons. This is p-type, so I've got holes. So here's my design. The next thing I want to do is I want to put a voltage across the whole thing. And you should be able to answer this question if it shows up on a quiz. So the question is, if I apply a voltage to this, where's the voltage drop? Well, obviously, if I have a circuit here, okay, and I've got a diode this way, and I've got over here a diode this way, and I put positive voltage on this side, which I'm doing, and negative voltage here, then the positive voltage will forward bias this diode, but reverse bias this diode. And so all the voltage drop will be across the reverse bias diode because it has the larger resistance, right? And so you can see that here. I put a voltage drop across this BJT here, and all the voltage drop is now across the reverse biased base collector for this, okay? Notice the Fermi levels are lined up for the emitter base, which makes sense because there's no voltage drop, so I should have no shift in the bands. And here, we basically have positive on this side, negative on this side. Positive pulls my bands down, negative pulls my bands up, and so you can see how the Fermi levels have shifted. So, now we've got our collector working, right? This is our collector. We said we wanted our collector reverse biased, so we're almost ready to make this device work. Okay? But the challenge is you know, what we've got to get holes here. So what could we do to inject some more holes from the P plus to the n-type material, and what could happen? Okay? And so what we'll know is that if we could just start injecting holes into here and get them over to here, they could drift out the collector. The problem is that all of our applied voltage is across the base collector here, right? So the question is, what else could we do to get voltage drop across the emitter and the base here to start injecting holes here by forward biasing this diode? What we do is we add a second voltage source. We have one voltage source here which reverse biases the base and the collector, so positive on the N, negative on the P, that's reverse biased, right? And now the collector's ready to collect by drift current. But importantly, what we've done here is we've added a voltage source here to the emitter and the base, which has now forward biased it. Positive on the P, negative on the N, that's forward bias. What that does, right, if I have positive voltage bands down, negative voltage bands up, that reduces the barrier. If this shifts down, there's less of a barrier for holes to diffuse over. High concentration of holes here, none here almost because it's n-type material. And so we start seeing, in terms of current magnitudes, an exponential increase in the number of holes which can diffuse over just like forward biasing a diode. Now, here's a key thing. We made the base width very small here. We purposely designed the base width so that it's narrow. So the question is, what's going to happen to the holes? They move over here, they show up here, and the question is, will they basically make it across to the other side or recombine? Well, because we made this base width so narrow, the holes don't have to go much distance to basically reach this cliff and fall off the cliff, right? And so very few of the holes will recombine. Most of the holes will make it across as drift current, and very few of the holes will recombine because the base width is so narrow, they don't have enough distance to find an electron to recombine with. Now, if WB was large, let's say we made WB really large, how would this change? Well, if WB was really large, you'd have such a long distance as holes tried to make it across here, they would all recombine, and then we wouldn't see what we see here, which is that my base current is really small and my emitter current is really large. That's the key point. That's what makes this a transistor. Because I made my base width small, okay, I can get electrons that are sitting in here, and because this is lightly doped and this is heavily doped on this side, I have very few electrons going this way versus holes going this way. And again, because the base width is small, the holes make it across. So I get a huge hole current, very large current through the device, but a very small base current. I'm bringing in electrons. Electrons are negative charge, so the current's in the opposite direction, and it's small. And you can see large current caused by a small current in the base. That's transistor amplification. One question you might be asking is how do the holes get across the base? That's a really good question. How do the holes get across the base? Well, if the holes didn't get across the base, what would be happening over time is I would start building up a huge excess of holes at this side, right? So I'd have basically a lot of holes on this side here, and none here. Well, you know already that if a forward bias diode builds up an excess of holes at one side of the diode, and a reverse bias diode has 0 holes on this side because this is the edge of the cliff and they all fall off, then I've got an excess here, 0 here, concentration gradient. Therefore, diffusion drives the holes across the base. Okay? And that will basically get them over to the collector where then they leave the device as drift current. Let's look at the design a little bit closer to make sure we can really appreciate why we want the base width so thin. So again, I said we wanted the base width thin. You can see that beautifully shown here in that same current plot we had of current through a P plus N junction. And we said that only out to a certain distance here, you have to go a certain distance before the electron current becomes large. And so if you look at holes diffusing across here, it's dominated by hole current. And the key point is that the closer you are here, the lower the electron current is. Basically, as you go further in, the holes are recombining, which means you need more and more electron current to bring in to recombine with those holes. Okay? So if I make my base width small, my width of this N-type material, I bring it in, and here's WB, I make it as small as possible, then the amount of electron current IB needed to recombine with holes is really small because there isn't enough distance for them to recombine. So now you can see also what we've done. We've basically taken the P plus N junction, cut off this material, and then you can see how you get a large collector current for a very small base current, and hence you get amplification of currents. You can kind of look at this in terms of the doping levels. Again, it's P plus N for the junction, and you have low N-type doping here in the N-type material. And so let's say, for example, that it's 10 to the 15th per cc for the electron doping in the N-type material. You could calculate, using the equations we know, right, that are easy to calculate for the semiconductors, that the diffusion length for holes would be about 100 microns. Remember, that was diffusion length was sort of the average distance a hole would go in a material before it recombines, right? Well, look at that, 100 microns for 10 to the 15th doping. And so let's look at the example of what WB might be. Well, typically, WB is only about 1 micron in a device like this. And so if our diffusion length is 100 microns and our base width is only about 1 micron, that tells you that, again, most of the holes can make it across without recombining, and that's shown directly by the ratio of diffusion length to the base width. Let's look at it one more way, and I think this will really help solidify. So let's look at all the possible currents going through our BJT in this diagram here. Okay? And again, remember that the emitter is where we inject the holes from a forward bias diode. The base, the term is historical because it was that chunk of germanium which was on the bottom of the first transistor. And the collector, it doesn't really do anything. It just sits there and collects holes, right? And our emitter current has to be equal to our base plus collector current. Of course, it has to be emitter current coming into here has to be equal to the currents leaving this portion of the device as well. Okay? So, let's look at this diagram and see if we can make sense of everything that's happening here. First, let's look at current component number 1 right here. These holes are injected by diffusion. And what are they going to do? Okay, so my question is for you, what are they going to do? Well, these holes are going to diffuse across the emitter base. So I inject these holes here. They will diffuse across the emitter base because I have an excess of concentration here, reverse bias diode, zero concentration here, concentration gradient, diffusion, right? 2, the holes reach the base collector depletion region, which is electric field, right? And they do what? Well, we know that they will drift to the collector because this is a reverse bias diode and the current flow is dominated by drift. So they will drift to the collector. Okay? Third thing, what are these holes doing here? What is this thing here, this 3? I have holes getting across to the collector, but I have some holes coming this way. This is representing the holes that are recombining with base electrons. And so some of the holes will not make it across. They will recombine with electrons. And so that's current component 3. But if we design this small with the right dopings and the thin base, then 3 will be much smaller than 2, and I can get good amplification. Let's look at current component number 4. These electrons coming in, what are they for? What are these electrons for? These electrons in 4 are basically to recombine with base holes. So if I have this many holes going this way that are recombining, then I better have the same number of electrons coming in to recombine with them to cancel out. Okay? Let's keep moving along. Number 5 here. These electrons, what do they do that are injected? Well, remember, this is forward bias, right? So yeah, I'm injecting holes this way, but if it's a forward bias diode, I have some electrons going this way, right? And so they are diffusing across the emitter base. However, remember, this is P plus and N. And so I have tons of holes this way, but because this is lightly doped, I don't have many electrons coming this way because, again, I don't have a big concentration gradient and there's not a lot of electrons. So that's important to remember as well. Last thing here, number 6. This is reverse biased. What are these coming from? This is just basically drift. This is really small. This is just the reverse saturation current across the diode. And remember, reverse saturation current is tiny, and so it's almost, for a BJT, not measurable compared to the amount of current coming through the collector due to normal transistor operation. Here's the key point. I cannot emphasize this enough. Remember, we designed this so that it was a P plus N junction for the emitter base. Therefore, 1 dominates over 5. Okay? That means that this current component dominates over this. Tons of holes, versus electrons diffusing this way. That's important. I want large emitter current for small base current if I want to get amplification. Okay? If they were the same, there would be no amplification. Second thing, I want WB to be much less than LP. I want my base width to be much less than the diffusion length for holes in the base. Diffusion length, how far they go before they recombine. And as a result, current component number 2 will be much greater than current component number 3, meaning that most holes will get across, very few holes will recombine, and again, the goal is to get big current through the device for a small current of the base, which has to recombine with these. So I want this current to be small, I want 5 to be small, and I did that by having lightly doped material here and heavily doped here. And I want this current to be small, and I achieved that by making the base width small. And it's important to remember, though, that 3 does not equal 0. I can make the base width small, but I will always have some current due to that recombination. So at this point, you can review what we've presented so far and take a break. Make sure you are solid on the starred items, as always, and you're able to answer also some of these questions. So you should be able to answer very readily. The emitter emits by being forward or reverse biased, and is the current drift or diffusion. The collector collects by being forward or reverse biased, and is it drift or diffusion? A third question that you should be able to answer is, we get amplification because there's a small base current that results in a large emitter current. Remember, small base current, large emitter to collector current. The base current is small and we get strong current amplification because of what? Well, that was everything I talked about on the previous slide, and you should be absolutely solid with all those design requirements.